Okay, and then normally it is for 1 to 10 years lah, right? And then for the long-term estimate is normally more than 10 to 50 years, okay, or more. Okay, so there is no exact solution because of the impact of war, okay, and so on. Okay, so I think I have gone through this, right? Forecasts are often based on the past census of the records. Okay, the census is the official survey of the populations. Okay, so every countries has doing it to estimate the populations. Okay, so to optimize the estimation, all possible informations regarding the anticipated industrial growth, local birth, okay, death rates. So these will be included in the calculations. Okay, so there will be something like a modeling to estimate, to run the estimations. Okay, so this is the short-term estimating, or known as trend-based methods. Okay, so in this method, in short, we have two methods. Okay, arithmetical progression and also the geometric progression. So I know that you have learned this in your math subject. Okay, these two progressions. Okay, so I'm sure you have some basic how to calculate. Okay, using these two formulas. Okay, so I think I will not explain further of the formulas. Okay, how to derive it. Okay, but this is the general formula. Okay, for the arithmetic. So y is equal to y2 plus y2 minus y1, t2 minus t1 multiplied with t minus t2. Okay, so this is the time that you are going to forecast. Okay, and there will be y1, y2, that is the population's number in the past. Okay, so you have two data, okay, and also the two time, okay, t1 and t2. Okay, and then for the geometric, so this we will be using ln, okay, ln y. So basically the formula, they are similar. Okay, you can see the difference. Okay, they are quite similar. Okay, so the next one is the long term. Okay, after this we will have two examples. One is for the short term prediction. The other one is a long. No, sorry. Oh yeah, one example for the short term lah. Okay, because for the long term estimation is going by graph. Okay, graphical prediction. Okay, so this we are not going to have any calculation for that. Okay, so but I will just show you how to estimate the trend. Okay, so this is the made by graphical comparison with growth rates. Oh yeah, I forgot to start the recording. Thanks, Vishalini. All right, I just saw that. Okay, so the population time curve of a given community can be extrapolated on the basis of trends experienced by similar and larger communities. Okay, so you can see later on the next slide, you'll see the graph of the population versus time curve. Okay, all the curves are coincident at the present population value of the city being studied. Okay, and then the city selected for comparison should not have reached the reference population value too far in the past, since the historical periods involved may be different. Okay. Okay. So this is the one. Okay. Graphical prediction. Okay, for long term. So you can see it from 45 here. Okay, maybe this is 1945. Okay, so from 45, 55, 65. Okay, until 2005. Okay, so this line, okay, this line is from the historical value, okay, historical population, okay, under study. So we have the value, okay? And then for the dotted line, okay, you can see there are 4 lines, okay, A, B, C, and D. Okay, so these are all the projected, okay, by using different estimation. Okay, so the estimation, so a slight different of the factors that you are taking into consideration. Okay, then you will have a different trend. Okay, for example, when the the uh, the birth rate, okay, the death rate, okay, uh, so it will affect the trend, right? So this is the growth curve for similar but larger cities. Okay. So this method is actually we used it to discover, okay, of the factors that influence the both lah, okay, present and also the past population, okay, whether it will be increasing or decreasing, okay. So with a slow increment of the population, okay, so normally it will be under the mean curve, okay, this one, okay, projected population. Okay, you can see that the line is different, okay, different pattern. Okay, so both C and D, it is a population with slower growth. Okay. So this is normally more complex. It also involves some mathematical modeling. Okay, so here are one of the example, okay, of the component of this long-term estimation. Okay, so the rate of population change is determined by some interactive factors. Okay, so like I mentioned just now, the birth rate, death rate. Okay, so other than that, we have immigrations, government policies, okay, associated attitudes, okay, and so on. The components of a population change, okay, can be linked together. Okay, so they have this formula. Okay. So this is only for your reference, okay, or for your information. Okay, so next, move on. We have this calculation for the population forecasting for short term. Okay, consider a city with the following population. Okay, we have two historical data, 1990 and 2000. Okay, and the populations. So this is 15,000 and 18,000. Find the population at 2010 using short-term arithmetic and geometric method. Okay. Okay, so for the first one, okay, so this is the formula. Okay, y is equal to y2 plus y2 plus y1 minus O divided by t2 minus t1 multiply with t minus t2. Okay, so we just substitute in. Okay, the calculation is quite direct and simple. Okay, so okay, since you have this, okay, the T1 is 1990. Okay, T2 is 2000. Okay, year 2000. Okay, and then you have Y1. The population is 15,000. Okay, Y2 is 18,000. Okay, so you are going to find the year in 2010, right? Oops. 2010. Okay, so Y2 is 18,000. Okay, plus Y2 minus Y1. Okay, T2 minus T1. Okay, so multiply with T minus T2. Okay, T is the new T, T, the one that you are going to find is 2010. Okay, so minus T2, T2 is 2000. Okay, so it is quite straightforward. Okay, just substitute all the values into the formula. Okay, then you'll get the population by estimation in year 2010. Okay, can anyone calculate and share your answer in the chat box? Okay, 21,000. Okay, 21,000. Okay, so this number is the population, 21,000 people. Okay, so all right, so I can see a same answer from means that you all got it. Okay, so those couldn't get this, you can try to calculate again. Okay, so the next one is the geometric. Okay, geometric is by using ln. Okay, this progression. Okay, so similarly, because the y, there are y and t values are the same. Okay, so I will just write ln y 2010. Okay, so we have ln year, okay, 18,000, right? Plus ln 18,000, ln 15,000. Okay, T2 is 2000, T1 is 1990. Okay, what T2 is 2010, T, sorry, T, okay, and then T2 is 2000. Okay, 2000. So at the end, you find the year 2010. So the answer for arithmetic and geometric, they'll be slightly different. Okay. Okay, Matthias got it, 21,600. Okay, thanks, Matthias and Kichen. Okay, so by arithmetic, you get 21,000 and geometric is 21,600. Okay, so a difference of 600 in 2010, in year 2010. Okay, so since this is by estimation, there will be no exact value, okay, for the population. Okay, this is by forecasting. Okay. Okay, next example is actually one example on the water usage. Okay, so this also involve of the population. Okay, so there's no formula for this water usage, but you can see the values, okay, the units. Then you can know how to find it. Okay, So normally we are going to find the water, the volume, okay, the volume of the water usage. Okay, you can see the example here. Okay, a community having a population of 250,000 in year 2000, estimate that its population will increase to 400,000 by the year 2020. Okay, so the water treatment facility can process up to 55 million gallons per day. Okay, MGD. Okay, the 2000 per capita water use rate, okay, was found to be 160 GPD. Okay, this is the year, okay, year 2000. Okay, estimate the water requirement in year 2020, assuming that the capita use rate remain unchanged. Okay, so means that the capita, okay, the use rate, but the population has increased. Okay, so even though the use rate remain the same, okay, remain as 160. Okay, but the population has increased, so the water requirement, okay, will also increase, right? Okay, so let's see. So this I have summarized the data. Okay, the data given. Okay, so in year 2000, the population is 250,000, and then this is the water use rate. Okay, 55 million gallons per day. Okay. Okay, and we have the water usage. Okay, 160 gallon per day. Okay, so this is the water from the water treatment plant. Okay, water treatment facility. So it can supply 55 million gallons per day. Okay, so let's see the part A. Okay, if there is no changes in the use rate, okay, if there's no changes in the use rate, so we can find the capacity. Okay, because the question is asking water requirement. Okay, means that it provides from the water treatment facility. Okay, so this is what we're going to find. So you can see the unit is in million gallons per day. Okay, million gallons per day. Okay, so we are going to find the water capacity. Okay, in 2020. Okay, 2020. Okay, so we have the population, right? 400,000 population. Okay. And then we have the water usage. So this is same as in year 2000 and 2020. Okay, so we are going to use this as well, 160. Okay, so 400,000. Okay. Okay, this is the population, and this is the water usage per capita, means per one person. Okay, per person. So times 160 gallon per day. Okay, so this unit will be in gallon per day. Okay, but you can the final answer you can make it the same, okay, into millions gallon per day. So you have to divide by 1 million. Okay, you can divide by 1 million so that your final unit is in million gallon per day. Okay, so do you get 64? So there's no formula for this one, okay? You just need to understand the question, okay? And then by using the data given, then you can find the answer. Okay, okay, thanks, Wei Han. All right, so it means that the water treatment facility or water treatment plant needs to supply 64 million gallon per day. Okay, for the to cut to 400,000 of people, okay, in the community. Okay, so let's see what is B. Okay, part B. Will expanded treatment facility be needed to accommodate this growth in population? Okay, is there any needs to expand the treatment facility? Okay. Okay, so you can see currently in year 2000, okay, the treatment water treatment plant only supply 55 million gallons per day. Okay, so now in year 2020, okay, so it needs 64 million gallon per day. Okay, so since the Q in 2020, okay, 2020 is greater than 2000. Okay, meaning that this 64 million gallon per day is greater than 55. Okay, so expansion is needed. Means that you have to upgrade the water treatment plant, okay, or the water treatment facility. Okay. Then part C, if revised plumbing codes were adopted during the period of growth, and if these changes resulted in an overall reduction in the community water use by 15%. Okay, okay. In short, okay, because of the plumbing, okay, then it reduced the water use rate. Okay, because of the plumbing codes. Okay, means that there's safe water. Okay, so water use rate becomes less than with lesser of 15%. Okay, what would be the water requirement in 2020? Okay. Okay, not enough space. Let me. Okay, hold on. Okay, so part C. Okay, so since now we have a 15% of reduction of the water use rate. Okay, so earlier the water usage in 2000, in year 2000 is 160. Okay, so the Q, okay, not Q. Okay, you can just write the water usage. Okay, in year 2020, okay, is equal to 160 gallon per day. Okay, 6 times with the 15% of reduction means that you times 85 over 100. Okay, 85%. Okay, then you get 54.4 gallon per day. Okay, so this is the water usage. Okay, with 15% reduction. All right. Then for the D, will expanded treatment facility be needed to accommodate condition in C? Okay. So this is similar to question B. Okay. So you can see the the Q is 55 in year 2000. Okay, and then in 2020, okay, 2020 it's 454.4. Okay, so the new capacity, okay, the new 2000, okay, is lesser than 2000, sorry, 2000. Okay, 2000. Okay, so which is 54.4 less than 55. Sorry, 160. Water usage. Okay, let me see the C again. Okay, over reduction. Okay, what would the water requirement in 2020? Okay, water requirement. Okay, so water requirement is this is the water usage. Sorry, this is the water usage. So here you get 136 gallon a day. Okay, yes. Okay, 136 gallon per day. Okay, and then we have to find the water capacity or the water supplier. Okay, so in gallons, a million gallons per day. Okay, so this is the Q in 2020. Okay, the new one. Okay, so this you can use. Okay, similarly here, because the population is 400,000. Okay, so times 136 and then divide by 1 million. Okay, so your final answer will be in million gallon per day. Okay, so that is the water supply. Okay, so this 136 is per person. Okay, per person. Okay, so here you get 54.4. Okay, so now this is correct. Okay, 54.4. Okay. So the new water supply is lesser than the one that in year 2000. So meaning that the expansion is not needed. Okay, expansion is not needed. Okay, you can actually see the difference. Both are also gallon per day. Okay, but this is the one that water supply from the water treatment. Okay, this part. the one that I put Q, okay, that is the water supply. Okay, so 55 million gallons per day, and this water usage is per person, okay, per capita. Okay, so if you have the population number, okay, you multiply it, then you get the water demand. Okay, water demand. Okay, so if the supply is lesser than the demand, the demand, okay, this is the demand, okay, the new population in year 2020, okay, so if the demand is lesser than the supply, okay, so the expansion is not needed, okay, since the demand is lesser than the supply, okay. So this example just help you to understand how we manage to estimate using the population, and then which link to the water treatment facility, okay, to supply the water. Okay, so we have to keep doing this from time to time, so that we will not face any water shortage in future. Okay, so the population forecasting is very important. Okay, we need to estimate the water use rate. Okay, any question regarding this example? Okay, all right, thanks. Okay, so the last slide is just a summary, okay, just to remind you all about how important it is to save water. Okay, because a water supply system, okay, will be, because all this while we are talking about the sustainability. Okay, so this water supply system will only be sustainable if it promotes in the both efficiencies and in the supply and also the demand. Okay, so and we also have some initiative to meet the demand for the water supply. Okay, if they prioritize the measurements, okay, to avoid the water wastage. Okay, you can see in some country they implement a higher water tariff. Okay, in Malaysia, because we always say that we have plenty of water. Okay, so the water tariff is low, and then we use it. We use the water for granted. Okay, we never appreciate the water. Okay, so some country they really did well in this part. So our country can still improve, okay, on this part, how to save the water. Okay, so a lot of experts already mentioned that in near future, okay, water shortage will be a big problem, a big issue. Okay. Okay, so just to share with you about this. Okay, so that is the end of this topic 2. Okay, right. Okay. Okay, before I continue to topic 3, let me share the attendance first. Okay, for today's attendance. Okay, I put it in the chat box. Okay, I hope I can finish the topic 3 today. Okay. It's not that long. Okay, can you all see my slide for topic 3? Okay, thank you. Okay, so now we'll go for the topic 3. It's about the water quality. Okay, so you can see the outline this topic. Okay, so first we'll go for the drinking water quality standard. Okay, so since this is the one that we are mentioning earlier, okay, one of the goal of water treatment, okay, to treat the water as it is potable, okay, means that it's drinkable. And then the second one is we'll talk about some of the common water pollutant that can be found, okay, in the water treatment plant, okay, when it's discharged, okay, and then we have the toxic water pollutants, okay. So the toxic water pollutants normally found when the water mixed with the industrial wastewater, okay. So then only it has the potential of having this kind of water pollutants. And lastly, we'll go for the pollution parameters and some of the laboratory tests. Okay. Okay. So this drinking water quality standard, okay, the national standard, okay, was established in 1990 by Ministry of Health, okay, in Malaysia, MOH, to provide a comprehensive national guideline to ensure the drinking water quality of the public water system. Okay, so this you can refer to this table, right? So you can see we have certain parameters, okay, that I listed out in this table 3.1. Okay, later on I will share you another list, okay, another list of a full list of this national standard, okay, for drinking water quality. Okay, so it means that it's not only we having this about more than 10 okay, parameters, okay, it's actually more, okay, we have a lot more parameters. Okay, and you can see the second column, okay, this is the recommended raw water quality with the acceptable value. Okay, so and the last column is the drinking water quality standard. Okay, so you can see the difference between these two columns. So this is the raw water quality. Okay, why we have this? Okay, why we have this recommended raw water quality? Because you know, in the water treatment plant, okay, we are having a similar treatment system, okay, a series of water treatment facilities. So, um, so if we have the raw water quality in a different standard, okay, or different quality, okay, so it means that you have to revise your water treatment facility. Okay, so if we have a standard, okay, a so-called standard, okay, then you only need some minor changes, maybe the chemical dosage, okay, and so on, okay, need to be uh, updated, okay, in the facility, okay, so that is the reason why we have this recommended raw water quality. Means that we will test the raw water quality first before let it flows into the water treatment plant. Okay, before the treatment started. Okay, and the last column, this is the drinking water quality standard. This is very important because the water, the final discharge of the water after treatment, okay, must fulfill all these criteria. Okay, for example, for the total coliform E. coli, okay, it must be 0 in 100 ml. Okay, so don't worry about this. Okay, what is total coliform, what is E. coli, it will be covered in this topic. Okay, I will explain it further. Okay, how are we going to do the test on what is the importance of this total coliform and E. coli, okay, in affecting the drinking water quality standard. Okay, and then we also have this turbidity. Okay, turbidity you can see is 5 NTU. NTU is the unit for turbidity. Okay, the unit's name. Okay, so acceptable means that it must not more than 5 for the turbidity. Okay, it can only be lesser than what listed here. Okay, and then for the pH, okay, pH is usually 6.5 to 9. Okay, and then color. Okay, color is 15 TCU. TCU means that it's a true color unit. Okay, true color unit. For color measurement, if you refer to the standard methods, okay, we have apparent and true color. Okay, different. So the test will be different as well. Okay, true color we will go through the filtration. Okay, before testing. Okay, that is the main difference in the color testing. Okay, and then chloride. Okay, the one that without a unit is in milligram per liter. Okay, milligram per liter. So 250 milligram per liter, and then hardness. Okay, hardness is actually hardness is not a health risk. Okay, it will not have any health risk. Okay, but it will cause some problems if the water having high in hardness. Okay, you learn about this in the next topic, topic 4. Okay, if I'm not mistaken, okay, in the physical or chemical treatment there. Okay, so you learn about hardness next week. Okay, hardness, if the water is having high in hardness, so it will have build up minerals. Okay, because normally it is caused by the some these minerals. Okay, these cations, the calcium and magnesium. Okay, is the main two components that causing this hardness. So for the material itself, it's caused by the something like the soap, okay, the detergent, okay. Okay, so when the water is having a high in the hardness, okay, so it will build up the minerals on the plumbing fixtures, okay, and then it will cause a poor soap and the detergent, okay. And then we have iron, aluminium, total dissolved solids. Okay. Okay. So for example, the total dissolved solids, okay, is coming from the agricultural runoff. Okay, agricultural runoff, the residential runoff. Okay, that having high in calcium, sulfate, okay, sodium. And lastly, we have these two, the chemical oxygen demand and biochemical oxygen demand. Okay, so this is also the under common pollutants. Okay, underwater pollutants. Okay, this I will explain further in the next coming slide. Okay, so this this national standard for the drinking water quality. It stated that the drinking water must be clear, okay, does not have any objectionable taste, color, and odor, okay. So remember in the first week and in the first lecture, I've shared you a news, okay, that saying that the water, okay, the river water having pollution, okay, and they did the odor test, okay. Okay, so it must be pleasant to drink and free from all harmful organisms, chemical substances, and also radionuclides in amounts which could constitute a hazard to the health of consumer. Okay, the quality of drinking water is measured in terms of its physical, chemical, and microbiological characteristic. So later on, we will group them into different. We have the different parameters under physical, chemical, or microbiological characteristic. Okay, so this is stated in the table 3.1 just now. Okay, so drinking water quality standard lists these characteristic and constituents with their recommended standard, which shall not be exceeded for maximum protection. So as I mentioned just now, it cannot be exceeded as what stated in table 3.1. Okay, so let me share you the list. Okay, the list of the okay, maybe I'll share later. Let me just show you first. Right. Okay. Okay, so this is the in PDF. Okay, I will share it later on. Okay, so this is the National Drinking Water Quality Standard by MOH. Okay, so you can see the total coliform, okay, turbidity, color, pH. Okay, this the one that I have extract. Okay, put it in the table 3.1. But other than that, we have others parameters in more details. Okay, for example, the minerals. Okay, and then some heavy metals. Okay, and some organic chemicals. Okay, so this I will share it later on. Okay, just for your reference. Okay. Okay, so for the water and wastewater characterization, okay, we have this break into this three groups. Okay, we have physical, chemical, and biological. Right? So for physical, is for example, color, taste, odor, temperature, turbidity, pH, solids, and also the alkalinity. Okay, and then for the chemical, we have organic compounds for BOD, COD, oil and grease, okay, total organic carbon. And then we have also the inorganic compounds, such as the nutrients, the minerals, and the metals, okay, like what I have shown you the full list just now, okay. And then we have the biological, okay, total coliform, okay, and we have the total coliform and E. coli, okay, and also the toxicology assay, okay, to test the toxicity of the water, okay. But this is not covered in this topic. Okay. So before this I think you all have taken one subject called environmental science and engineering, right? So you have been introduced with some of the tests, okay? For example, the BOD test, okay, the dissolved oxygen test, okay, solid, okay. So you have some background, okay, how to what are those, okay? What are the some of the parameters, okay, in the common water pollutants here? Okay, so here in the common water pollutants, we will discuss seven of them. Okay, so the biodegradable organic matter, solids, okay, oil and grease, okay, E. coli, residue, chloride, ammonia or nitrogen, okay, and also the phosphorus. Okay, so the first one is the this biodegradable organic matter. So it relates to the dissolved oxygen. Okay, so it established a lower limit to protect the propagations of fish and other aquatic life, enhance recreation and reduce odors resulting from decomposition of organic matter, and maintain a suitable quality of water for treatment. Okay, so this is the importance of dissolved oxygen, because normally oxygen is less dissolved in the water. Okay, so but with a certain amount, it can protect the aquatic life. Okay, and not only that, it will also can help to decompose, because we have the microorganism living in the water. Okay, so it can help to decompose the organic matter. So that's why when the dissolved oxygen level is lower, okay, meaning that some bacteria, okay, they couldn't survive, okay, and then the water will getting more polluted because they cannot dissolve the organic matter. Okay, so it's always relate, the BOD test is always or the dissolved oxygen level is always relates to how polluted is a water source. Okay, all right, the primary pollutant that associated with DO depletion is carbonaceous BOD. Okay, if you okay, so talking about this carbonaceous BOD, okay, the total BOD, okay, this is something about the biochemistry, okay, carbonaceous BOD plus this nitrogenous BOD. Okay, so this is how we get the BOD, the general formula. But the main pollutant that associated with the this DO depletion is caused by the carbonaceous BOD. Okay, only a small part of the nitrogenous BOD, because this is consumed by the organic nitrogen or ammonia, okay, that convert it to the from nitrite to nitrate. Okay, so it only consume a small amount of oxygen, dissolved oxygen. Okay, so the main pollutant or the main cause of the DO depletion is by carbonaceous BOD. Okay, so sedimentation of suspended solid can cause a buildup of decomposing organic matter in the sediments. Okay, so this is another cause by how is the DO being consumed. Okay, dissolved ammonia can cause DO depletion by nitrification. So this is the one that I mentioned just now. Okay, but this is only a small fraction of dissolved oxygen being consumed. Okay, so the sources of the DO depletion, okay, or the root cause of the DO depletion is by the Usually it's by the excessive algae growth, okay, which caused by the phosphorus and nitrogen that flows into the water source. Okay, so it always relate to others common water pollutants. Okay, so they have the interactions. Okay, so the DO also reduced by the decomposition of organic matters, but that we cannot avoid because this is happen in naturally. Okay, it happened naturally. Okay, because the microbes needs food and oxygen. Okay. All right. So the next is the solids. Okay. So here we only discuss about the suspended solids. Okay. So since these suspended solids, it will also affect the colors, the turbidity, right? And not only that, it will interfere with the transmission of light. Okay, so once the light cannot penetrate into the water, okay, so it will cause a lot of problem. Okay, so it will interfere with the recreational use and aesthetic enjoyment, affect the growth rate and resistance to the disease of fish, reduce the amount of the food available. Okay, so some aquatic plants, they couldn't produce food because of uh, the blockage of the light. Okay, and then it will damage the invertebrate population. So this is a chain effect. Okay, when there's a problem with the transmission of light due to suspended solids. Okay, so the solids should not reduce the depth of the compensation point for photosynthesis activity by more than 10% from the seasonally established norm for aquatic life. Okay, so because of the photosynthesis activity, so the sources of this causing the suspended solids is due to normally is the silt, the clay particles, okay, even the algae itself, okay, and then the fine organic debris, okay, so that is also the cause of suspended solid. So those doesn't dissolve in water, okay, exist as a particulate. Okay, and then for oil and grease, okay, oil and grease, the sources are petroleum derivatives, and then the fats from vegetable oil and meat. Okay, so this will cause the um, this oil and grease. Okay, so and then the problem is the taste and odors. Okay, next is the E. coli. Okay, E. coli is the um, it's actually indicate the possible presence, okay, of the pathogenic organism. Okay, this is one of the under pathogens. Okay, um, okay, I will explain in more in details, okay, about this E. coli because we have a last section talking about the E. coli part. Okay, so I'll go through it briefly first. So the most E. coli strain are harmless, but some stereotypes can cause serious food poisoning in their host. Okay, E. coli bacteria must absent in 100 ml sample. Okay, like you see just now in the table 3.1, okay, the E. coli quantity must be 0 in 100 ml. Okay, I will also explain how we carry out the test, okay, later on. Okay, so for the E. coli source, okay, is mainly from the human waste, human or warm-blooded animals waste. Okay, the feces. Okay. Right. Next is the residual chlorine. Okay, chlorine resulted from disinfection of wastewater effluent, which is very toxic to fish. So that's why during the disinfection, okay, the dosage must be calculated perfectly, okay, not to have any waste, okay, or residue to be discharged, okay, out from the water or wastewater treatment plant, okay, because they are very toxic. And these chloroamines are formed when chlorine reacts with ammonia. Okay, so the excess or the residue chlorine will form with uh, will react with ammonia. Okay, to form these chloroamines. So reduced by adding reducing agents such as sulfur dioxide. Okay, it can be the solution now. Okay, is by adding the reducing agents. Okay. So the sources for residue chlorine. So normally it's because of the excess disinfection, over disinfection, and it will cause residue chlorine to be happen. Okay. So next is the ammonia. Okay. So actually here should be the under nitrogen. Okay. But because nitrogen, we have different sources. Okay. So we have the free ammonia. Okay. We have the biodegradable and non-biodegradable soluble organic nitrogen. Okay. Or in particulate form. Okay, of the organic nitrogen. So most commonly, this nitrogen pollution is due to the free ammonia. Okay, because the ammonia can exist in aqueous solution as the these ammonium ions, okay, or ammonia gas. Okay, so we can see here the reaction when the ammonia dissolve in water. Okay, it will form ammonium ions. Okay, so this is the common form. Okay, that this how we get the nitrogens. Okay, and this ammonia is very toxic to fish and other aquatic animals. Okay, the concentration increasing with pH, increasing temperature. Okay, all right. So the sources for ammonia is usually coming from the fertilizer, okay, or animal and human waste, okay, and sometimes it happens when the gas exchanger, because in our atmosphere, okay, it has the nitrogen gas, okay, so the gas exchange will actually form this free ammonia gas. Okay, so this is also the sources. Okay, the sources. Okay, pH of the surface water. Okay, protect the fish life and control undesirable chemical reactions such as dissolution of metal ions in acidic water. Okay, so most of the living organism, okay, they are both for animals, okay, or plants, they are very sensitive to the pH changes. Okay, so for example here, okay, many substances increase in toxicity with changes in pH. Okay, so when the pH became alkaline, okay, then the ammonium ions, okay, will form a poisonous ammonia, okay, because the pH can actually affect the solubility or toxicity of the chemicals in water. Okay, so the sources of the pH change, okay, or the causes is due to the chemicals involved. Okay, normally by the agricultural runoff, okay, the wastewater or industrial wastewater discharge, okay, to the water stream. Okay. Okay, and the last common water pollutants is the phosphorus. Okay. Okay, the key nutrient that's stimulating the excessive plant growth, okay, both weeds and algae in lakes, estuaries, and also the slow-moving rivers. Okay, cultural eutrophication is the accelerated fertilization of surface water arising from phosphate pollution associated with discharge of wastewater and agricultural drainage. Okay, so the sources is actually from the uh, this fertilizer as well. Okay, because we use it for the plant growth. Okay, but when we use it extensively, okay, the excess of this phosphorus will flow into the surface water. Okay, so that is also the main cause of the phosphorus pollution. Okay, so the next one is the toxic water pollutants. Okay. So it includes some organic chemicals and inorganic ions, okay, especially heavy metals. Okay, so some example of the inorganic ions, for example, like the, oops. Okay, for example, calcium, okay, and then zinc, uh, potassium, sodium, okay, so that is the inorganic ions. Okay. Okay, and then for heavy metals, for example, the mercury, cadmium, okay, arsenic, okay, those very commonly found in the water sample. Okay, criteria of the priority toxin, okay, is they will uh, have this environmental hazard, okay, and it found in polluted water. Okay, normally it's the industrial wastewater. Okay, when it mixed with the surface water. Okay, so here are some of the commonly found toxic water pollutants in surface water. Okay, the majority of the toxic pollutants are categorized into these 10 groups. Okay, so for example, the halogenated aliphatic hydrocarbons. Okay, we have phenols. Okay, phenols also very commonly found. For example, in the disinfectant, in the normally in the household disinfectant. Okay, some surgical antiseptic. Okay, or even in the mouthwash. Okay, you to rinse your mouth. It has a small number of the phenols. Okay, contain. Okay, because we use it for disinfection. Okay, then we have monocyclic aromatic hydrocarbon, okay, and others. So you can see uh, it can cause damage to the central nervous system and liver, okay, cause skin irritation and internal organs. Okay. Then some you can also see it is carcinogens. Okay, carcinogen means that it will cause cancer. Okay, cause cancer, and then it will bio-magnify in the food chain. Okay, bio-magnify means that it will increase the level of the toxicity in the food chain. Okay, because it will accumulate. Okay, it cannot be degrade easily. Okay, so that uh, magnify means it's getting higher and higher. Okay, so it has increased level of the toxicity. Okay. So most of them, these 10 groups, they are normally from organic chemicals. okay, because we use a lot of organic chemicals to as a solvent, okay, as a solvent. So this water contamination with these toxic water pollutants, okay, that mixed with these organic chemicals, it will normally cause, for example, like leukemia, okay, cancers, any neurological damage, okay, or even tumor, okay, and others very severe disease, okay. For common water pollutant, that is not that serious, but it will affect uh, the consumption, okay, when normally when we use it for consumption. And toxic water will poses a very hazard to our health, okay. So that is the main difference between common and toxic water pollutants. Okay, so next is this, we call it a standard methods handbook. Okay, so these common parameters that we use in the water quality analysis, that includes the one that we have discussed earlier, the TET, total solid, suspended solid, okay, dissolved oxygen, BOD, COD, even the biological test, the coliform bacteria, it's all stated in these standard methods. Okay, so if you have chance to go back to the campus, okay, or enter the lab, the chemical lab, so normally you can see this handbook, okay, the standard methods handbook, okay. It's like an encyclopedia lah. It will have all the very detailed procedures or the reagents or the chemicals that needed uh, to carry out the test, okay. So even it has also the calculations and then uh, the errors, okay, and so on. Okay, everything is described in very details, okay, in the standard methods. Okay, so I'll go a few more slides before we take a break. Okay, let me finish the solid test first. Okay, so the first one that we are going to discuss is the solid. Okay, solid test, how we have the experiment, okay, how to carry out the test, okay, and also the calculation. Okay, here we can see the first one is because under solids we have total solid, we have suspended solid, we have volatile solids, okay, dissolved solids. Okay, so we can see in this first part, okay, or first section, we have the total solids and suspended solids. Okay, so the concentration of total solids, the unit is in milligram per liter, okay, or sometimes it's reported as gram per liter, is the weight of dry solids, okay, divided by the sample volume. Okay, and total volatile solid is the weight of dry solid minus the weight of fixed solid divided by the original sample volume. Okay, so this I will show you in the formula later on. Okay, so first look at how we do the experiment. Okay, so you have normally we have a evaporation dish, okay, or drying dish. Okay, so we have a number of names. Then you fill this drying dish with water or wastewater sample, and then you record the volume as V. Okay, and then you put in an oven, okay, and dry it at 103 degrees Celsius. So normally it's 103 to 105 lah. Okay, 105 degrees Celsius. So let the water to evaporate. Okay, then you get the dry solids in the dish. Okay, then uh, you weigh it again to get the mass, okay, the weight. All right, then the next step is if you are going to find the fixed solids, okay, then you need to put in the furnace. Okay. So here you put it in an oven. Okay. And here, because you need a higher temperature, so you have to put it in a furnace. Okay. So again, you get those volatile solids to burn off, okay, and left the fixed solids in the dish. Okay. So you can see the formula here. Okay, you have total solid WS, okay, in gram or milligram, divide by the original volume. Okay, volume, the water sample volume. Okay, in liter. Right. So and then for the total volatile solids, okay, total volatile solids is the WS minus WF. Okay. So because here we still have contains the volatile or the some moisture, okay, then we minus the fixed solids, okay, divide by the volume, okay, the original volume. So that is the formula to find total volatile solids. Okay, so this is the total solids part. And then for the suspended solids, okay, suspended solid means that those particulate, okay, that is suspended in the water. Okay, so so you can see the difference between total solid and total suspended solid is that we have a filter. We will use a filter funnel, okay, to pass through the water sample, and then we do the same steps, okay, or the same procedures to get the filtrate, okay, to get the filtrate and heat it in an oven and furnace. Okay, so this time is not putting in a dish. Okay, we will heat the filter paper. Okay, so that is the only difference between the total solid and suspended solid. Okay, and the name will be follow. Okay, for example, here is the total suspended solid, and here will be the we find the volatile suspended solid. Okay, so we have this suspended solids here. Okay. All right. The next one is the formula. Okay. The formula. Okay. So from the experiment, you can find the total solid, right? Oops. You can find the total solids and total suspended solids, okay, from the experiments. And then the total dissolved solids, normally we will use the formula to find, okay. So it means that total dissolved solid is equal to total solid minus total suspended solids, okay. So these two are from the experiment, okay. You calculate from the experiment, okay. Same as the volatile dissolved solid. So total volatile solid and the volatile suspended solid can be calculated from the experiment. Okay. Then the volatile dissolved solid you can use this formula. Okay. So any questions so far for the solid test? Is that clear? Okay, thank you. Okay, next we will have one example, okay, for this solid test. Okay, how to calculate all the solids. Okay. Okay, so you can see the solid analysis is one of the most widely used parameters for assessing the water quality. Use the following data for calculating the total solids, total volatile solids, dissolved solids, total suspended solids, and total volatile suspended solids. So a sample volume of 200 ml was used in performing all solid analysis. So meaning that in this part, okay, where you want to find the total solids and total volatile solids, you are using 200 ml of water sample. Okay, same as here in the suspended solids part, you flow through 200 ml of the water sample through this filtration funnel. Okay, so both also using 200 ml. But in actual test, normally we will use a lesser volume of water. Okay, but it depends on the in the raw water sample whether it has a lot of suspended solids or not. If it has a lot of suspended solids, normally we will use a lesser volume. Okay, so maybe like 50 ml, or even it is it if you know that it has a lot of solids, okay, suspended solids, then you can even dilute it. Okay, but this is not mentioned here. Okay, you can dilute your sample and flow through this filtration funnel. Okay, so here you can see the mass of the evaporating dish. Okay, so it means that this is the empty dish. Okay, 25.334 gram. Okay, and then we have this the mass of the evaporating dish plus the residue. Okay, after evaporation at 103 degrees Celsius. So this is the after cooling from the oven, after you take it out from the oven. Okay, then this is the mass. And the third one is the residue after ignition. So this is after taking out from the furnace. Okay, so 25. So you can see the mass here is always lesser than the second one. Okay, it cannot be this higher than the second one. Okay, because this will further burn off the volatile solids. Okay, so that's why here will be always smaller. Okay, and here the fourth data is the mass of filter. Filter actually is the filter paper lah. Okay, it's 1.5 gram. Okay, and then this is after drying. Okay, and this is after burning in the furnace. Okay, so similarly here is smaller than after taking out from oven. Okay. All right. So now we can find the total solids. Okay. So remember the formula is the difference of the mass. Okay. The difference of these two mass. 25.439 minus 25.334. Okay, 25.439 minus 25.334. Okay, divide by 200 ml. Okay, the volume is 200, right? 200 ml. But you can change it to liter, so 0.2. Okay, and this is in gram, so you can change it to milligram. Okay, so is that clear? Why we need to multiply with 1000, and here why it's 0.2. Okay, so this is liter, so here is milligram. Okay, so your final answer will be in milligram per liter. Okay, so do you get 525? 525 milligram per liter. Okay, okay. All right, next we can find the volatile solids, right? Okay, so some people they write volatile solids, but it is understood, or you can write total volatile solids. Okay, so it doesn't really matter. Okay, so for the volatile solids, then you have to use the difference between these two masses. Okay, divide by 200. Okay, 25439 minus 25385. Okay, so similarly multiply with 1000, divide by 0.2. Okay, and you get 270 milligram per liter. Okay. Okay, so next we have the suspended solids. Okay, so total suspended solids. Okay. So we have 1.5103 and 1.5439. Okay, 1.5439 and 1.5103. Okay. Okay, then we have volatile suspended solids, 1.5439 and 1.5199. Okay, so here you get 168 and here is 120. Okay. Okay, since you get all the values, okay, so for the dissolved solids part, you can use the formula. So total dissolved solid. Okay, so if you want to find the total dissolved solids, you can use the total solid minus TSS. Okay, 525 minus 168. Okay, same as for the volatile dissolved solids. So 270 minus 120. Okay, so this is how we get all the solids. Okay, by using experimental result and also the calculation. Okay, the formula. Okay, can you all get these values? The final answer. Okay, this one is 357 and 150. Okay, yes. Okay, good. Okay, so now we will take a short break, and then we'll continue for the rest. Okay, the BOD formula. Okay. We'll continue at 10:40. Okay, 10:40. Yeah. All right. I'll share the drinking water standard here. Okay, welcome back. Okay, I hope everyone clear with this calculation for the solid. Okay, so I have shared the drinking water quality standard in the chat box. Okay, you may refer to it for the full list. Okay, and then for the table 3.1 is actually just a summary lah. Okay, I summarize or extract it from the full list. Okay, because we are going to focus on certain common water pollutant as well as some of the toxic water pollutants. Okay. Okay, next is the dissolved oxygen. Okay, so this dissolved oxygen will relates to the BOD test and the COD test. Okay, the one that we are commonly used to test the a quick test to know whether the water is polluted or not. Okay, so first of all, you can see some definition of the dissolved oxygen. Okay. Okay, so yeah, as I mentioned earlier, the oxygen is a rather insoluble gas. Often the limiting constituent is in the aerobic purification of the waste and natural water. Okay, the minimum concentration is required for the survival of higher aquatic life. Normally the minimum is 1 to 4 milligram per liter. Okay, normally. And the solubility ranges from 14.6 milligram per liter at 0 degrees Celsius to about 7, okay, at 35 degrees Celsius. Some of the important parameters in biological treatment processes, okay, so why we use the dissolved oxygen as an indicator, okay, because we will use it when the aerobic or anaerobic organism. So these two are under the biological process. Okay, so we can have two types of microorganism. Okay, so one group is aerobic, the other one is anaerobic. So aerobic usually is the one that consume the dissolved oxygen. Okay, and anaerobic is in a confined place. Okay, without oxygen gas. Okay. So we use it to indicate which organism is predominant. Okay, and we can indicate the suitability for the growth of sensitive organisms such as the nitrifying bacteria. Okay, so whether it is suitable to grow. Okay, to dissolve the nitrogen. Okay, or ammonia. So dissolved oxygen as a function of temperature, you can see with the increase of the temperature, okay, the dissolved oxygen level will go down. Okay, dissolved oxygen level. And also the apart from temperature, okay, the pressure, okay, at a higher elevation, okay, the oxygen level will also reducing. Okay, you can see at 3,000 meters above the sea level for the same temperature. Okay, so it went down. Okay, so this is some of the relationship between the temperature and also the elevation with the oxygen level. Okay. Okay, so here we have two methods or two measurements for to find the amount of gas that in the organic or inorganic matters, okay, demands in the water. Okay, we have BOD, biochemical oxygen demand, and COD, chemical oxygen demand. So I will explain what is the difference between these two from the next slide. Okay, so you can see The first one is the BOD test. Okay, BOD test. So BOD is the quantity of oxygen gas that consumed by a microorganism while they decompose the organic matter under aerobic condition, okay, of the wastewater and polluted water. So you can see there are few keywords here, okay. So there must be a aerobic condition, okay, by the aerobic organism, okay, to decompose the organic matter. Okay, they will use up the oxygen gas. Okay, so these are some of the few keywords. Okay, so for the this BOD conditioner, okay, so it must be a BOD. Okay, normally we use a 5-day BOD lah, or we put a BOD 5 here. Okay, BOD 5. 5 means 5 day. Okay, we can also have a BOD 3, okay, or another day. Okay, so depends on the condition. Okay, but this 5-day BOD is more accurate, okay, than it is also commonly used. Okay, to define the strength of the municipal wastewater, to evaluate the efficiencies of the treatment by measuring the oxygen demand remaining in the effluent, and to determine the amount of these organic pollutants in the surface water. Okay, so the condition is they are using 300 ml of BOD bottles. They are incubated. Okay, incubated means it's sealed. Okay, it's sealed and then keep in a fixed temperature at 20 degrees Celsius. Okay, other than that, for BOD 5, okay, so we'll keep it for 5 days. Okay, incubated for 5 days and in a dark place. Okay, in a dark place. So there are 5 conditions for the BOD test. Okay, so first one is a 300 ml. Okay, and then they are incubated or sealed. Okay, they are kept in a 20 degrees Celsius. Okay, they will keep for 5 days. Okay, 5 days, and in a dark place. Okay, normally we put in an incubator or a fridge. Okay, fridge that you need to adjust the temperature to 20 degrees Celsius. Okay, so these 3 conditions. Okay, so like I just mentioned just now, the BOD 3, for example, BOD 3 days, so the temperature will be 30 degrees Celsius. Okay, so they also have a list for different condition for different BOD tests. Okay, so I will not further discuss about the different type of BOD, but this is BOD 5 is the one that commonly used. Okay, so we'll just focus on this part. Okay, so you can see the test. Okay, so let's look at the bottom one first. Okay, the bottom, the diagram B. Okay, B. Okay, so this is the aerated dilution water at 20 degrees Celsius. Okay, so you put so this BOD bottle is plus minus 300 ml. Okay, so you cannot get perfectly 300 ml. Okay, for the volume. So normally it will have some errors. Okay, so but it's at 300 ml plus minus. Okay, so and then you put the polluted water sample. Okay, into this BOD bottle for the test. Okay, so this is what we normally do for a water sample. Okay, a polluted water sample. So, and you can see in the diagram A, it has much more. Is much more complicated. For example, we have the seed organism. Okay, so this diagram B is without seed. Seed, so we call it unseeded test. Unseeded test, and this is a seeded BOD test. Okay, and here this part is the BOD reagent. Okay, we have the BOD reagent or chemicals. Okay, so you can see in the list here. Okay, in the list here we have the buffer for phosphorus or phosphate. Okay, buffer for phosphate, and then we have this ammonium chloride, magnesium sulfate, calcium chloride, ferric chloride. Okay, so these are the BOD reagent. Okay, so this for both water, okay, whether it is seeded or unseeded, you still need the BOD reagent. Okay, it didn't mention here, but it is we'll put it in the bottle. Okay, together with the aerated water. Okay, the reason why we need the aerated water is that we need to keep the water, because after that we will seal it, right? We will seal and incubate it in a dark place. So we need to keep the microorganism to stay alive, okay, to use up the oxygen gas and degrade the organic matter. Okay, so we need to have a concentrated oxygen gas. Okay, that's why we use aerated dilution water. Okay, for both water. Okay, the only difference between these two bottles is that this we have the seed microorganism to be added into the bottle. Okay, so the reason is you can see here preparation of BOD test on wastewater sample. Okay, A is for wastewater. Okay, B is polluted, but it is a surface water. Okay, so meaning that in this bottle it actually contains the microorganism already. Okay, so that's why we doesn't need to add the seed microorganism. Seed means is the microorganism. Okay, so for wastewater usually it is the condition is not suitable for the microorganism to survive. Okay, that's why it has no microorganism or very less. Okay, so that's why we need to add the seed microorganism into the wastewater sample. Okay, so that is the difference for unseeded and seeded BOD test. So for the calculation, it will also have some difference. Okay, for the formula part. Okay, BOD. Okay, so this I will not go through it. Okay, so this you can see the general formula. Dissolved oxygen plus the organic matter degraded by the bacteria. Okay, it will. The end product is the CO2 gas and the biological growth. Okay, so this is the formula for unseeded BOD. Okay, so you can see the BOD. Okay, formula is DO1 minus DO2. DO1 is actually the initial dissolved oxygen. Okay, so it means that after you have prepared this bottle, okay, you add up the aerated water. Before you add the aerated water, you have to put the water sample, right? You have to put a certain amount of the water sample, let's say 10 ml. Okay, you put 10 ml here, then you can add up, you can fill up the bottle. Okay, so let's say this bottle is 300 ml, so you have to add 290 ml of aerated dilution water into this part, into this bottle. Okay. And then after that, you have to measure the dissolved oxygen level. Okay, you put a DO meter, okay, immerse it, and then get the DO. Okay, so that is the DO1. Okay, initial DO. So after that, let's say this is a VOD5 test. So after 5 days, okay, you take out from the incubator and then remove the tap, the cover, okay, and then you measure the DO again. Okay, so that is DO2 or final DO. Okay, some formula they write it as DO initial minus DO final. Okay, so it's the same. Okay, they are the same. So divide by dilution factor P. Okay, so the P, the formula is sample volume also divide by the water volume. So in the example just now, I use 10 ml, right? So I use 10 ml of the water sample, and then the bottle volume is 300 ml. So 10 divided by 300. Okay, that is your P. Okay, that is P. Okay, so the formula is quite simple for the unseeded. Okay, just the DO initial minus DO final divide by 10 over 300. Okay, if the water sample is 10 ml. Okay, so the bottle volume here is always 300. Okay, for the formula, we assume as 300. Okay, but in the experiment, maybe it is, let's say it is 305 ml. Okay, then you have to write 305. Okay. All right, so the next one is the seeded. Okay, so you can see if you have the seeded, then you have the this B1, B2, and F. Okay, this is the called the seed correction. Okay, since you added the additional microorganism, okay, so you have to consider the seed correction. Okay, so the equation for calculating the BOD from this, okay, BOD is equal to D1. Okay, so the same thing here, initial DO minus the final DO. Okay, so initial is always higher than the final because the microorganism will use up the oxygen. Okay, so initial is always higher. Okay, same as for the sample in the seed. Okay, in the seed bottle there, right? Okay, maybe I draw it out, then it will be clearer. Okay. Okay, so just now, this is the BOD bottle. Okay, so you just add 10 ml. Okay, we just add 10 ml of the water sample. Okay, and then for this one, okay, let's say this is the BOD bottle. Okay, so you add 50 ml of the water of the wastewater. Okay, and this wastewater has no seed. Okay, we assume it has no seed, so we add 1 ml of seed. Okay, so this bottle we name it as a sample. Okay, because we have added the wastewater sample. Okay, then we need to have another bottle. Okay, the same BOD bottle, and where we add 10. Okay, let's say it's okay, let's say we add 10 ml of seed. Okay, and this we call it a blank sample. Okay, this is the bottle without wastewater. Okay, so we need to prepare 2 bottles for 1 reading. Okay, so of course this volume of the wastewater, the volume of the seed, they are all by assumption only here. Okay, in the actual experiment, you need to study, you need to interfere. Okay, what is the BOD? Okay, roughly lah. Okay, what is the BOD? Infer, not interfere. Infer the BOD. Okay. So okay, so let's say this is the volume that I have added in for the seeded BOD test. Okay, so by definition, you can see okay, what is the D, B, F, and P. Okay, so D here is the dissolved oxygen. Okay, readings in the sample. So you have the initial and the final. Okay, so this no problem, right? This D1, D2, and then the B1, B2 is the one that in the blank sample. Okay, so we call it a seed control here. Okay, seed control. So also the same, you measure the initial DO and the final DO in the blank bottle here. Okay, And this F, okay, F, F is equal to, if you look at the definition, okay, ratio of seed volume in diluted sample to the seed volume in the control, in the seed control. Okay. So if from the numbers that I've written here, so what is F? Anyone? What is the value, or what is the ratio of F? Okay, 1/10. Good. Correct, 1/10. Because 1 ml from the sample, diluted sample. So this is called a diluted sample because we have 50 ml of wastewater plus. So here the volume is 51, right? 51 ml. So the whole volume is 300. So 300 minus 51, then you get another volume. Okay, when you calculate for the P later on. Okay, so but the F here is 1/10. Okay, the 1 ml seed in the sample water to the seed control sample here, 10 ml. Okay, so Yihao is correct. Okay, 1/10. And P. Okay, P is the ratio of the wastewater volume. Okay, so here is 50 over 300. Okay, 50 over. So here you just consider the volume of the wastewater. Okay, without the seed. Okay, so 50 ml. Okay, as long as you can identify what is the volume used in the sample and what is the volume used in the blank or the seed control, okay, then you can calculate, okay, the BOD. Okay, we'll have an example later on. Okay, I will show you again how to calculate it. Okay, so here is the conditioner for the BOD test for both, for seeded or unseeded. Okay, at least 2 milligram per liter of DO should be used during the test period. Okay, so the dissolved oxygen should be used, meaning that for BOD5, okay, let's say for BOD5, the initial BOD, okay, you measure the initial and the final, the difference must be more than 2 milligram per liter. Okay, the difference must be more than 2. If it is less than 2, so the result is invalid. Okay, invalid, then you cannot calculate it. Okay, because it's a wrong test. Okay, so either you have put 2 liter of the 2 liter or too much of uh, the water sample. Okay. Okay, and the second condition is at least 1 milligram per liter of DO should remain. Okay, so at the end means the dissolved oxygen, final dissolved oxygen must be at least 1. Okay, it cannot be 0 point something or totally 0. Okay, remain at the end. Okay, so this is this part is the D1 minus D2. Okay, and this is D2. Okay, only look at the D2. It must be at least 1 milligram per liter. Okay, must be more than 1 milligram per liter. So this one is D1 minus D2 is more than 2. Okay, for a valid result. Okay, so remember, if this value is not fulfilled, okay, so it cannot be calculated. Okay, you cannot calculate and tell that it is the BOD value. Okay, no, it's not fulfilled, then you cannot calculate it. Okay, it's not valid. Okay, so the next slide will tell you when do we need to add seed? Okay, when do we need? Okay, so treated or chlorinated wastewater. Okay, so normally after treatment, okay, the microorganism will be killed, okay, or not exist anymore. Or for the chlorinated wastewater, you know the chlorine is for the disinfection, so it kills the bacteria, right? So these are the example when we need to do the test, the BOD test, okay, we need to add the seed, okay, so that we can do the BOD test correctly, okay, get the result correctly. Okay, how do we determine the amount of wastewater added to the BOD water? Okay, so this is the guideline. Okay, this is the guideline. For example, just now I mentioned that how many ml of the water sample need to be added. So, so of course, if you don't follow this guideline, okay, you can prepare a few sample with different volume, okay, until you get the BOD test becomes valid, okay. So initially, when you put a different volume, okay, you might not get the result because of this condition, okay, because of these two valid test condition. Okay, so here only a guideline, 5 ml for untreated wastewater with BOD range from 120 to 420. So this is the result from the past, okay, or from the past researcher, okay, that by estimation is about 120 to 420, then you can use 5 ml of the water sample. Okay, then 50 ml for the effluents with the BOD range 12 to 45 and so on. Okay, so this is only the guideline. What is the use of aerated water? Okay, just this one I have mentioned earlier when preparation here. Okay, why we need the aerated dilution water. Okay, so to provide the DO for aerobic decomposition means that to provide the oxygen for the aerobes, the microbes. Okay, if it is unaerated, the DO will depleted before the organics are fully oxidized. Okay, then you underestimate the BOD reading. Okay, so this is also very important for the preparation. Okay, so continue for the seeded, okay, seeding. Provides microorganism to oxidize the organic matter not required for municipal waste, biological treated effluents, or surface water sample. So you can see some of the example that example of the water sample doesn't need seed. Okay, so you know the municipal waste is that contains microbes. Okay, municipal waste. And then the biological treated effluent. Biological means that it is treated by the microbes. Okay, so it is saturated with the microbes. Okay, and also the surface water sample like the river water, they are naturally have the microorganism. Okay, so doesn't need any seed for the BOD test. Okay, some industrial waste may require seeding. Okay, so normally it's the industrial waste, but not all. Okay, but not all the industrial waste need seeding. Okay, it depends. Okay, so normally it's those exotic or difficult to degrade. Okay, with high temperature, extreme pH, toxic substances. So you can see all these conditions, they are not suitable for the microorganism to survive. Okay, so this condition will normally need seed when you need to do the BOD test. Okay, so you just imagine that seed is the microorganism, and if the condition of the wastewater or the water sample is not suitable for the microorganism to survive, then you have to add the seed. Okay. All right, so we have two examples, right? Three examples. Two examples. Okay, so the BOD test unseeded. Okay, so this is unseeded BOD test calculation conducted on a polluted surface water sample by adding 200 ml, okay, to 300 ml of water by filling with dilution water. The initial DO measure 7 milligram, final is 20, so 3.2, okay, calculate the BOD. So first of all, you need to see the values, you need to see the readings, whether it fulfill the validity, okay. So we can see the DO initial is 7, final is 3.2, okay. So this 3.2 is, okay, this 3.2 is more than 1, okay, so it's valid, okay, and then 7 minus 3.2 is greater than 2, okay, so it is also valid, okay. So you need to check first, okay, before you calculate, okay. So because this is the example, okay, normally we will just use the one that is it is valid, okay, but in an actual experiment, this is the first thing that you need to check, okay, the final DO and the difference between the DO, okay. So BOD, this is a 5-day BOD, so we can write BOD 5 equal to 7 minus 3.2 divide by, okay, it used 200 ml divide by 300. Okay, so this is the calculation to find BOD 5. Okay, so do you get 5.7? Okay, okay, thanks Ziao. All right, so I think is no problem, right? Calculation. If you know the definition of the formula, then you should be no problem. Okay. Okay, the next one is the seed BOD. Okay. Okay, so here I have summarized it into 2 sections. Okay, for the seed control and also the water sample, so that you can read it easier. Okay, unlike in your tutorial, okay, you have your tutorial 2, okay, with this BOD calculation. Okay, tutorial 2 means next week. Okay, so you can see the question. Okay, normally it is lumped together. Okay, all the information. Okay, for the seed control, the volume of seed added to the bottle is 6 ml, and then the initial DO is 8.2, DO is 4.8. Okay, so again, you have to check the validity first. Okay, and water sample is seed is 2 ml, sample is 30 ml, initial DO 8.1, final is 3.2. Okay. Okay, so this is the answer. Okay. So maybe you can try first, see whether you can get it or not. Okay. In this question, it didn't tell you that this is a BOD 5 or what. Okay, so you can just write BOD. Okay, so normally if we know that it is a BOD, it's a 5-day test, then you can write BOD 5. It's a 3-day test, you can write BOD 3. Okay, so not always BOD 5. Depends on the condition. Okay, so BOD, we have the formula initial DO minus final, so 8.1 minus 3.2. Okay, then minus the seed. Okay, seed is 8.2 minus 4.8. Okay, and then you have to multiply with the F. Okay, F, that the seed that you use in the sample, okay, is 2, and then the seed used in the seed control is 6, right? Okay. So some might make mistake lah, okay, if you without the bracket, okay. So just be careful when you do the calculation. And the sample is 30 ml, total is 300. Okay. So you should get the answer 37.7. You can check, you can double check the calculation. Anyone got it? 37.7. Okay. Okay, please try, because sometimes I I might make mistake also. Okay, just double check. Okay. And also good for you, you check on, then you know what mistake that you make and you do the calculation. Okay, so the next one is the COD. Okay, COD test. Okay, COD is a measure of the oxygen equivalent of the organic matter susceptible to oxidation by a strong chemical oxidant. Okay, so both also using the oxygen gas, okay, to find, okay, how much oxygen, dissolved oxygen needed to degrade the organic matter. Okay, the only difference here is the BOD test we use the microorganism, okay, the aerobes, okay, but in chemical oxygen demand we use the strong chemical oxidant by performing the oxidation. Okay, so similar but using different methods. Okay, so later on you know what is the major difference. Okay, also what is the good and bad in both methods. Okay, the test procedure is to add the measured quantities of standard potassium dichromate, concentrated sulfuric acid, silver sulfate. Okay, so these are the COD reagent. Okay, COD reagent, and measure of volume sample into the flask. Okay. Okay, a blank sample of deionized water is carried. So sometimes we use deionized, or sometimes we can replace by the distilled water. Okay, doesn't really matter. Carry through the same COD testing procedure to compensate for any error that can result due to the presence of extraneous organic matter in the reagents. Okay. Okay, so you can see the keywords here is it will oxidize all the organic matter. So organic matter, actually we have biodegradable as well as non-biodegradable. Okay, but in this COD test, it will oxidize all the organic matter. Okay, in BOD we only degrade the one that is biodegradable. Okay, so there are different. Okay, for BOD and COD. And since this COD test can oxidize all the organic matter, so usually the COD is always higher than BOD for the same water sample. Okay, it's always greater than BOD. Okay, so COD test. Okay, we have this formula. Okay. So actually COD test, this is only one of them. Okay, only one of them. Actually, we have different methods. If you refer to the standard methods handbook, Okay, we have a titration method. Okay, we have a calorimetric method. Okay, or we have the digestion method. Okay, so different methods have different calculation. Okay, so this is only one example. Okay, using the calculation. So this is using the ferrous ammonium sulfate. So this is by titration method. Okay, titration. Okay, application of the BOD and COD testing. Okay, so most common BOD is the most common parameter to define the strength of untreated and treated municipal and biodegradable industrial wastewater. Okay, to determine the oxygen required and the tank sizing for the aerobic treatment. So this is the application. Okay, once we know the BOD readings, okay, we can design, okay, for the tanks, tank sizing for the, you remember the activated sludge tank, okay, so that is the aerobic treatment, okay, based on the BOD loadings. Okay, to quantify the quality of an effluent, okay, so this is what we normally do for test to test the water quality, okay, of the effluent. To evaluate the water pollution by biodegradable waste. Okay, so the keywords here is you can only evaluate the water pollution by biodegradable waste. Okay, so this is very important. Okay, when we know what is biodegradable, then we can go for the cheaper way. Okay, which is the aerobic treatment. Okay, aerobic treatment, biological treatment is always the cheaper option. Okay, so when we know that the wastewater or the water has more biodegradable waste, okay, by performing this BOD test, then we can um, treat the water, okay, by biological process. Okay, so that is the application. Okay, for COD, okay, it is to define the strength of the industrial wastewater that are either not readily biodegradable or contain compounds that inhibit the biological activity. Okay, so because some water sample, okay, they inhibit the biological activity, so the BOD test is not accurate. Okay, you cannot get accurate result for BOD. Okay, then we can go for COD test. Okay, and another advantage in this COD is that it is more rapid. Okay, because it's only take including the preparation will be about 3 hours. Okay, about 3 hours, and it is reproducible compared to BOD. Okay, so it is more common now. Okay, so the main thing is very fast. Okay, we can save a lot of time if we know the total organic compound. Okay, the both degradable or non-degradable. Okay, but the drawback is that we cannot find what is the non-biodegradable or what is the only biodegradable organic matter. Okay, if we want to know. It does not distinguish between biodegradable and non-biodegradable organic matter. Okay. So that is the BOD and COD test, right? Okay, any questions so far for the BOD and COD? Whether the test procedures, the calculations. Is it clear? Okay, okay. We'll revise again. Okay. We will have a revision class in week 7. Okay, so if you have anything which is not clear, you may ask during that time. Okay, so next we'll go for the last section, okay, which is the waterborne disease. So it always deal with the biological characterization, okay, and we want to know what is the waterborne disease, okay. So many human diseases are transmitted by the feces of an infected person getting into the mouth of others person, which known as fecal to oral route. Okay, so normally the disease is always coming from the waste. Okay, the waste. Not directly lah. Okay, when the waste gets polluted the water source. Okay, then when you consume the water without properly treated, then we have the chance, okay, to get the disease to be transferred. Okay, so other routes we have inhalations, penetration through the skin, okay, by others these microbes. Okay, some of the diseases are endemic in form, okay, which is constantly present in a particular region or country. Okay, so we have normally we have 4 groups of pathogens. Okay, viruses, bacteria, protozoans, and helminths. Okay, which is worms. Okay, so this is the picture of the microbes, okay, bacteria, viruses, protozoan, and helminths. Okay, so here in this part, we will focus on one of the microbes, okay, or under the pathogens group, okay, because the pathogen is the one that caused the disease. Okay, so we were focusing on pathogen, but since pathogen have 4 main groups, okay, so this is nearly impossible to identify every microorganism that exists in a water sample. Okay, because but we know that pathogen is the disease-causing agent, so we have to find a suitable indicator. Okay, so here we have one which is called this coliform bacteria. Okay, we use it as an indicator for the potential of the presence of pathogens. Okay. So in the public water supply or the reclaimed water, the water we use are not tested for pathogens to determine the microbiological quality. Okay. So the laboratory for individual pathogens, okay, usually it is difficult to perform, okay, not reliable, and then the pathogens are present in small numbers, okay, for individual pathogens. So we normally test for a whole group, okay, whole group. So the microbial quality is based on testing of an indicator. Okay, we use these terms, which is indicator organism. Okay, so which is the microorganism that presents. Okay, so when it is present, then it has the potential. Okay, that the water is polluted with the pathogen. Okay, we are not going to test the pathogen individually. Okay, every group individually. There are a lot of tests. Okay, there are a lot of tests, and it's very expensive and takes a lot of time if you measure every single pathogens. Okay. Okay, so here we use the coliform bacteria, which is an indicator organism of the fecal contamination. Okay, so because most disease, okay, is coming from the fecal contaminations. Okay. However, this presence indicates the possible presence of pathogens. Okay. So types of coliform bacteria, we have, you can see this diagram. Okay. So the first circle, okay, is the total coliform. Okay, total coliform. So in every microbiological test, we will go for from one by one. Okay, we will test the total coliform. Okay, so if it's present, then we will only go for the second cycle. Second circle, which is the fecal coliform. And if this present again, then we'll go for the E. coli test, because E. coli is the one that the only one that has the possibility to have bringing the disease. Okay, so if one of them, the total coliform or the fecal coliform, is a negative test, okay, then we will stop there. Okay, means that the water is safe. Okay, safe from this E. coli. Okay, but this test is always is not always 100% accurate. Okay, because this is by statistical um, um, means that it is by statistical, so it's not 100% that we can guarantee that the water is totally free from E. coli. Okay. So here are some of the definitions. What is the total coliform bacteria? What is fecal coliform bacteria? And E. coli. Okay. So if you read it, you can see that the total coliform bacteria, they are commonly exist in the environment. Okay, either soil or vegetation. Okay, and they are generally harmless. Okay, so this is very important. They are generally harmless. So uh, if a lab detects only total coliform bacteria, the source is probably uh, environmental and fecal contamination is unlikely. Okay. However, if the environmental contamination can enter the system, the pathogens could get into. Okay. So it is important to find and resolve the source of the contamination. Means that, okay, if we find it, it doesn't mean that the water is dangerous to be consumed. Okay, but it has the possibility that the pathogens could go into the water system. Okay, so we have to find out whether it is contaminated or not. Okay, that is in short. Okay, then you can see the E. coli. E. coli is a subgroup of the fecal coliform group. So most E. coli bacteria are harmless and exist in the intestine of human and warm-blooded animals. However, some strain can cause illness. So like I said just now, if you do the individual test in the E. coli, okay, some bacteria they are harmless, but some they can cause illness. So to be safe and to save time and save the cost of the testing, we will test it as a whole. Okay, we'll test the whole E. coli group. Okay, so if the water sample found that the E. coli exists, so it has the potential that it will cause illness or bring disease. Okay, it's not saying that once E. coli is detected, the water is totally not consumable. Okay, so only some strain can cause illness. So generally they are still safe lah. Okay, harmless. Okay, only certain strain can cause illness. But to be safe, once the E. coli is detected, then we will need a further treatment. Okay, or retreat the water. Okay, in the coliform bacteria, we have three tests. Okay, we have three tests. So fermentation tube techniques, membrane filter techniques, present absence technique. Okay, so I'll go through it one by one. So this fermentation tube techniques, okay, so okay, I'll just explain what is the like the chemicals, okay, we have in this fermentation tube techniques, we have, yeah, this fermentation tube techniques has another name. Okay, I almost forgot. So some books they use this multiple tube, okay, fermentation. Okay, multiple tube. So it's actually based on the principle of dilution to the extinction. Okay, means that we use a different type of dilution. Okay, until we found zero. Okay, of the total coliform. Okay, so this actually involves three test phases lah. Okay, which is the presumptive, confirmed, and completed test. Okay, so these fermentation techniques, we use this lauryl tryptose broth. Okay, and then okay, maybe I show you the diagram. Okay, it will be easier to understand. Okay, so we can see here we have a different tube. Okay, different tube. Normally, so like I said just now, is by dilution. So let's say this is the original sample. Okay, so you can have for example 10 ml. Okay, or you can use 1 ml, or you can use 0.1 ml. Okay, and each test will have 5 tubes. Okay, 5 tubes, 5 tubes. Okay, so this diagram is just showing one of them, okay, one of the tube. Okay, so you can see the just now these chemicals that added, okay, the lauryl tryptose broth, okay, then okay, you put it into an incubation at 35 degrees Celsius. Okay, 35 degrees Celsius. So if there is no growth, okay, how we see the growth? You will have the gases, okay, bubbles. Okay, if there's no gases, okay, then it is a negative test. So negative test means that in the total coliform, okay, the total coliform, it is no coliform was detected. Okay, means that the water is safe. Okay, so but if it is a positive, okay, with gases, okay, then you need to go for the second test, which is the fecal coliform. Okay, so here we will add the EC medium, okay, and then go for the incubation again at 44.5 degrees Celsius, okay, for 22 to 26 hours. Okay, so this is 24 hours here. Okay, so after incubation for 22 to 26 hours, okay, then again you see the changes. Okay, if no gases, then it's a negative test, so means that it has no E. coli. And if it is a positive test with gases, okay, then we will check the MPN numbers, most probable number. Okay, so this is by estimation, statistically. Okay, so maybe I can show you the. Okay, let me show you the one table. Oops. Okay, so this MPN tables is under this to find the coliform per 100 ml sample. Okay, so remember in the table 3.1 just now for the drinking water quality standard, it shows that for the drinking water quality it must 0. Okay, 0 in 100 ml. Okay, so this all this number is for 100 ml of sample. So for example, just now you can see the number here. Okay, 10 ml, 1 ml, 0.1 ml. Okay, and these values are all the positive tests. Okay, so each 10 ml, 1 ml, and 0.1 ml, you have 5 tubes. Okay, you have 5 tubes. So for example, okay, for example, in the 10 ml, you have detected three tube has a positive result. Okay, and then in 1 ml, you have one test, one tube positive, and then 0.1 ml, you also have one tube is positive. Okay, then the MPN will be 14. 14 in 100 ml. Okay, so this is how we read the MPN. Okay, so you can see up to 5 tubes. Okay, the result is up to 5 tubes. So let's say 5 out of 5 10 ml tubes, okay, they are positive. Okay, 5 out of 5 the 1 ml, okay, are positive, and then 4 tubes are positive in 0.1 ml. So the MPN is 1,600. Okay, so this is the value, okay, which generate statistically, okay, by estimation. Okay, so this is the how we read the MPN. Okay. All right. So the second technique is the membrane filter. Okay. Membrane filter. Okay. So I'll show you the diagram. Okay. So again, this is the suction flask. Okay, which connect to a pump. Okay. So the water will go through the this membrane filter. Okay, membrane filter, and then it also have the culture dish with this M endo medium, okay, to let um, the microbes to survive, and also for the color changes. Okay, so after incubation at 35 degrees Celsius, okay, so if there is no colonies, okay, then is negative test. So if you see the colonies, then it's a positive. So something like this. Okay, coliform colony. Okay, so this is by color changes. Okay, and the membrane filter that having here, okay, is normally 0.45 micrometer. Okay, 0.45 micrometer. So the bacteria will retain on the membrane filter when the water pass through the filter. Okay, so the bacteria will stay here on the filter, and if with this condition, with these nutrients or medium, okay, it will start growing after incubation. Okay, if the coliform exists, okay, then this is the positive result. Okay, so this process, this experiment is very fast, okay, to detect the coliform, but you cannot get the E. coli. Okay. So normally you need a quick test, and you can go for the membrane filter techniques. Okay. If you want an accurate result to get the total coliform, the E. coli, then you can go for the this fermentation tube. Okay. Then we also have the last technique, okay, which we call it a present absent technique. Okay, so this test is more commonly used now, okay, and also it is fast. Okay, you can determine the coliform bacteria and also the E. coli. Okay, and also we will use the MPN to get the result. Okay. Okay. Okay, I think I have one video. Huh? Okay, we still have time, right? Okay, I have one video to show you the present absence method. Okay. So you can watch the video and then. Okay, wait. Okay, I mean you can watch the video first and then you can read the steps. Okay, so that you can understand it better.
The IDEX family of coliform and E. coli tests, ColiLert, ColiLert 18 and ColiSure, can be used with IDEX's QuantiTray and QuantiTray 2000 products to provide quantitative results. The following steps outline how to use ColiLert or ColiLert 18 with a QuantiTray. To perform the ColiLert and ColiLert 18 QuantiTray methods, you will need the following materials: sterile 100 milliliter vessels, ColiLert or ColiLert 18 reagent, QuantiTrays, a QuantiTray sealer, one or more QuantiTray rubber inserts, a temperature-controlled incubator, UV protective eyewear, a 6-watt 365 nanometer ultraviolet lamp, ColiLert QuantiTray comparator, and a most probable number MPN chart. All of these materials are available through IDEX. First, collect your water samples as described in standard methods for the examination of water and wastewater, or according to your local regulations. Next, turn on the QuantiTray sealer. The amber color light will illuminate. Wait approximately 10 minutes for the green ready light to illuminate, indicating that the sealer has come to operating temperature. Place an empty QuantiTray rubber insert on the input shelf of the sealer, with the large cutout facing away from the sealer and the overflow basin facing up. Next, carefully separate one ColiLert or ColiLert 18 snap pack from its strip, taking care not to accidentally open the other packs. Aim the snap pack down into a 100 milliliter sample and open it by snapping back the top of the score line. Be careful not to touch the opening of the pack. Cap the vessel and shake it thoroughly to dissolve the reagent powder. The powder must dissolve completely and the foam allowed to subside when using QuantiTrays. Open the bag of 10 QuantiTrays by tearing the labeled end and clip the bag closed to store unused trays. You may label the paper side of the QuantiTrays with a felt tip indelible marker as desired. Do not use a ballpoint pen. Hold the QuantiTray at the very top with the well side facing your palm. Push the very top of the QuantiTray in with your free hand while squeezing the tray into a complete circle. Then relax your hand to form a U. Open the QuantiTray by carefully pulling the foil tab away from the plastic side, being careful not to tear the tab. Avoid touching the inside of the tray. Pour the reagent sample mixture directly into the QuantiTray, avoiding contact with the foil tab. Allow the foam to settle. Place the filled QuantiTray onto the rubber insert, making sure that the tray is properly seated, with each well of the tray in its corresponding hole. Push the rubber insert into the sealer until the motor grabs the insert and begins to draw it through the sealer. Be careful to keep hands, hair and clothing clear of the tray shelf during sealing. In approximately 15 seconds, the sealer will distribute the reagent and sample mixture into the QuantiTray wells, seal the wells, and eject the sealed tray. If at any time you wish to reverse the motor, for example if a misaligned tray is accidentally fed into the sealer, press and hold the reverse button. However, do not reverse the motor once the rubber insert has been drawn fully into the input slot. You may run multiple rubber inserts consecutively in your sealer, allowing you to seal a large number of trays very quickly. Once the quanti tray is ejected from the sealer, remove it from the rubber insert and incubate the quanti tray at 35 degrees C, plus or minus 0.5 for 24 hours if you're using ColiLert, or 18 hours if you're using ColiLert 18. If applicable, incubation temperatures may vary slightly according to your local regulations. Note that you do not need to use a water bath for either test when using quanti trays. When incubating quanti trays, you may stack trays up to 10 high, but do not place them in a boxed shape, as this restricts airflow in the incubator. Once the test is fully incubated, read the results by comparing samples to a ColiLert quanti tray comparator. If the sample in the well is colourless, or less yellow than the IDEX comparator, the sample is negative for total coliforms and E. coli. Wells with a yellow colour that is equal to or greater than the comparator are positive for total coliforms. If a well is yellow, look for E. coli by shining an ultraviolet lamp on the sample in a dark environment, staying within 5 inches, 12.5 centimetres of the sample, and shining the light away from your eyes. If the sample fluoresces at an intensity equal to or greater than the comparator, it is positive for E. coli. If there's no fluorescence, or the fluorescence is less than the comparator, the sample is negative for E. coli. Be sure to count all wells that contain any sample, including the large overflow well at the top of the quanti tray, even if they're only partially filled. Once you've counted the number of yellow and fluorescent wells, refer to the quanti tray MPN table provided to find the most probable number of coliforms and E. coli. For example, this quanti tray has 6 yellow wells. Refer to the 6 positive well line on the MPN chart to see that the most probable number is 6.4 total coliforms per 100 millilitres. Since this tray had 5 yellow and fluorescent wells, refer to the 5 positive well line on the MPN chart to see that the most probable number is 5.3 E. coli per 100 millilitre. Be sure to dispose of positive samples according to local regulations.
Okay, so you can see the present absence method or techniques, right? So you can see the color changes after taking out from the incubator. Okay, so if it's a yellow color, then that is the total coliform. Okay, and you have a different format of the MPN table. Okay, so just now that I show you for the fermentation, okay, that is for 5 tubes with the dilution. Okay, and this MPN for present absent is simpler. Okay, so you just need to identify how many we call it wells. Okay, the square. Okay, the wells. How many yellow color? Then you just refer to the MPN table, and you can get the MPN values. Okay, and then for the E. coli, you need to pass it through the UV light. Okay, like in this, you pass through the UV light. Okay, so if it turns the yellow color into the bluish with glows fluorescence, okay, then it is a positive test for E. coli. Okay, so again for the E. coli test, you can also refer to the MPN table, okay, to find that how many E. coli in the water sample. Okay, so that is how you test, okay, this present absence technique. Okay, both also use the MPN table. Okay, so lastly is the okay. So this is only some general information about the pathogenic E. coli. Okay, So this is a strain that is pathogenic to humans. Usually it's caused by contaminated ground beef, raw milk, unpasteurized fruit juice. Okay. Okay. So the indicator test. Okay. Yeah, so only one indicator test is used instead of numerous tests, okay, for the pathogen. So here we will choose the fecal coliform, okay, in this topic, okay. All right. Any question? So out of these three techniques that I have introduced, only the membrane filter cannot detect the E. coli. Okay, but it is a quick test. Okay, to know whether the water contains total coliform, okay, or fecal coliform. Any question? Okay, good. Okay, so now we still have a few minutes more. I just want to remind you all that for the assignment, I have seen Dr. Lee had posted the Excel sheet for you all to fill up the group mates, okay, your group members' name and the details, okay. So for CI program, you go for the CI Excel, and then there's CL, then you go for the CL Excel, okay. So that is one. Then the other one is about the midterm. Okay, midterm test since last week, I get a few feedbacks from the class and also by email, okay, from some of you. Okay, so at the end, we have decided that we couldn't make it at any time in the weekdays, right? From because initially I put 10:30 to 12:30 for on Friday, and then someone cannot, right? Because you have class, and then Friday 2:30 to 4:30 also cannot. So seems like, and then Tuesday and Wednesday because we have the tutorial, okay. So some groups are affected, so I would like to have the midterm test on these days, okay, the Wednesday and Thursday. Okay, so what we can do is so the only option now is we can have it after 5. Okay, then it can be at any days. Okay, so Thursday, because you have the tutorial until 5, okay, one of the group until 5, so Thursday is out. Okay, so what I suggest is you can choose Monday, Tuesday, or Friday. Okay, Monday, Tuesday, Friday, 5 to 7. Mattis, what do you mean? 5:30 p.m. You want Friday 5:30?
No, because last time the previous discussion we made was you say 5:30 p.m. Friday. Yeah, that I remember. This is what I recall.
Yeah. Because after I think twice, because no difference. If we put on Friday, then how about Monday or other days? Okay, Monday and Tuesday. If it's 5 or 5:30, is it okay for you all? Seems okay, right? Because after 5 is no more class. Okay, unless you have class after 5, then you should let me know. Okay, so I will put the date. I will put the day here. Okay, midterm test. Monday, Tuesday, or Friday. 5 to 7. Okay, so I put it in the chat box so that everyone can see. Okay, then we'll only decide on Wednesday. Okay, on Wednesday. Then after that, I will let you all to fill up the Google form. Oh, same week Tuesday test. Okay, so Tuesday is out. Okay, Tuesday is out. So I need a lot of feedback from you all. Okay, so that everyone can make it. Okay, Monday you have class 5 to 7. Okay. Okay, so Monday and Tuesday is out. Monday, Tuesday. Stop the recording first.